So for the rest of this section, I just wanted to talk about some definitions, some theorems, and just general discussion of things that are going on here. So in the previous example, we had, this should be P inverse AP, but in the notes it's actually swapped. So just keep that in mind when you're reading the notes that I sort of swapped some of like the places of the inverses that I did with this video. Just keep that in mind. Everything's correct, but I just talked about things in a little bit different of a way that led to inverses being in different places. But anyway, so in our example, we had that P inverse AP was equal to a diagonal matrix, which is simpler or better than our original matrix, which was like all ones everywhere and then zeros along the diagonal. And the reason that this is better is because it tells us something about eigenvectors and eigenvalues, for example. And that's something that we won't get to until a little bit later in the semester, but I digress. So that leads to a definition. We say that a map F or a matrix, there's a way to define diagonalizable for a matrix. So we say that a map F is diagonalizable if there is a basis B such that the representation of F with respect to B and itself is a diagonal matrix. So this is the exact situation that we had in the previous example. The representation of our map F with respect to B and itself was a diagonal matrix. Okay. And what this definition means for matrices is it's equivalent to saying that there is an invertible matrix P such that PA P inverse is a diagonal matrix. So you could have also said that P inverse AP is a diagonal matrix, and it doesn't change the definition at all. Where you put the inverse doesn't matter because P is invertible, so you could have just replaced this whole thing with like Q, which was equal to P inverse, and then you'd have like QA, Q inverse, or whatever. So it doesn't really matter. But so the inverse could go here or it could go here in your definition. Okay, so new definition. For same size matrices, A and M, they don't have to be square, but this definition says that A is matrix equivalent to M if there are invertible or non-singular matrices, P and Q, such that M is equal to P times A times Q. So a couple observations about this. First, matrix equivalent matrices represent the same map with respect to appropriate pairs of bases. This is because P and Q are non-singular matrices, therefore they are change of basis matrices. So A and M, so like A represents a map F with respect to some pair of bases, and then multiplying by change of basis matrices on the left and right just changes the representation of that map with respect to those bases. So just multiplying on the left by P and Q just changes the bases, but it does not change the map that you're representing. Okay, well, I should also mention matrices can represent more than one map, but the point is that these two matrices will still represent the same map, just with respect to different pairs of bases. Anyway, next point, which is pretty useful, is to recall. So we've already talked about left multiplication of invertible matrices, but the same discussion applies to right multiplication of invertible matrices as well. So left and right multiplication by an invertible matrix corresponds to performing row or column operations on your matrix A that you're starting with. So we already showed this for like row operations. You can multiply by an invertible matrix on the left, and that'll represent row operations. And multiplying by an invertible matrix on the right corresponds to column operations. And therefore, if A and M are matrix equivalent, which means that M is equal to P times A times Q for invertible matrices P and Q that are multiplying by A on the left and right. So these are matrix equivalent if and only if there are row and column operations taking A to M. So here's an example. The matrix 1, 0, 0, 0 is matrix equivalent to 1, 1, 0, 0 because you could do a column operation to go from this matrix to this one. In particular, you could add column 1 to column 2 and get this. And so there is a set of column operations that takes you from him to him. However, those matrices are not row equivalent. And the reason being, if you were to do any row operation to this, the right column will always still be a column of zeros. You could add multiples of this row to this row or vice versa, but that's never going to change whether or not these are all zeros. You could scale rows by any constant that's going to keep these zeros, and you could swap rows and that'll also keep them zeros. So there are no row operations that take you from here to here, so they are not row equivalent. As a bigger example, here are two rank 3 matrices. They're both in reduced echelon form. I could do some column operations to the first matrix to get to the second matrix. In particular, I could treat this pivot 1, or I could use this, and I could add -2 times this column, and add that to this column to make this 2 a 0. And similarly, I could use this pivot to make this 4 a 0, and then this column would just be a column of zeros, which I could just swap with this column, and I get our matrix on the right. And so that gives us a general theorem. Any m by n matrix of rank k is matrix equivalent to the m by n matrix whose first k diagonal entries are 1 and all other entries are 0. So I would have k ones along the diagonal corresponding to the rank of our matrix that we start with, and everywhere else is just going to be a 0. And so the proof for that is like not so bad, because we already know that we can put a matrix into reduced echelon form. If it's rank k, then it would have k pivots, and you could use those pivots in the same way that we did in this example to make all entries to the right of those pivots equal to 0, and then you would be left with k pivots. So here we had 3 pivots, and then a bunch of other rows and columns of zeros. And you could just do row and column swaps to get to your matrix, which looks like this. So a corollary to that is that two matrices are matrix equivalent if and only if they have the same rank. So if you're rank k, then you're matrix equivalent to this matrix. And if a different matrix is the same rank, it's also matrix equivalent to that. Therefore, they're matrix equivalent to each other. Okay, so one last example. We can use this corollary to classify equivalence classes under matrix equivalence. So there are 4 equivalence classes of 3 by 3 matrices under matrix equivalence, and they correspond to the matrices of ranks 0, 1, 2, or 3. You could have any of these 4 ranks as a 3 by 3 matrix, and so therefore there are 4 equivalence classes because every matrix is row equivalent to one of the following representatives. So representatives can be chosen to be the 0 matrix, all zeros except a 1 in the first entry. You could have 2 ones along the diagonal and zeros everywhere else, or you could have the identity matrix. And these are all just exactly what this matrix here is representing just for the 3 by 3 case, and they're representing ranks 0, 1, 2, and 3. So hopefully that made sense. This is like take 10 of this video, so hopefully you appreciate it, and hopefully this is useful